Welcome back to another video with us here at LMD and STEM Academy. In this video, we will be working through the June 2023 Physics Unit 2 Paper 2. So we're on question 2, which is a question from Module 2. And it says that one application of an operational amplifier, or an op-amp for short, is that of a comparator, right? The figure below shows an op-amp comparator circuit. So this is what the circuit looks like whenever we're using an op-amp as a comparator, right? Okay. So the first question is asking us to write an equation to show the relationship between the output voltage V out, this guy, and the input voltage V1 and V2. Okay? All right. So we're going to write an equation. So here's our equation. The equation is that our output voltage V out, this guy here, is equal to the gain, which is written here as VAV, voltage gain, times the difference in the inputs. Okay? So something that's worth pointing out here is that the AV is our voltage gain. All right? That's voltage gain. That's what that stands for. And then the V1 is the voltage at this is your, which one is this? This is your non-inverting input. So that's your non-inverting input. That's where it's positive. Whatever you put in is what's going to go through, right? That's non-inverting, that one. And then the V2, this one, is your inverting, right? That's your inverting input. So you see whatever you put in there is going to get inverted. That's what that minus sign means. So your V2 input is your inverting input. So your inverting voltage. Okay? So just keep those things in mind. We're going to always be coming back to these, okay? So your V out is equal to your voltage gain times the difference between your non-inverting input voltage and your inverting input voltage, okay? All right, so let's move ahead. Okay, so using the equation in A part 1, briefly explain how a comparator works, okay? So we're going to use this equation, so we're going to bring it back, and we're going to use that to explain how a comparator works, right? So the word comparator, right, means that we're comparing two things, right? That's what comparator means, and really what we're comparing within the context of this op-amp setup is that we're comparing two voltages, okay? We're comparing two voltages. That's what a comparator is fundamentally. It's comparing two voltages, specifically your two input voltages, comparing your V1 to your V2. Okay, so now that we have that out the way, just some terminologies here as what comparator could mean, right? We're going to go ahead now. So here's how we explain how the comparator works, right? Well, there's a potential divider that is used to fix one of the input voltages. So for example, we might be fixing our V2, which we said earlier, our V2 was our, let's just write it, let's just label it on here, that we said that our V2, because it's going to the inverting amplifier, that's our inverting voltage. So that's our inverting input voltage. Right, so that's what V2 represents. And so what we're saying is that we're going to use a potential divider to just like lock this one in, right? Can't change. It's set. And when we set it, we're going to call it our reference voltage. So we're always going to refer back to that one. So we're comparing what V1 is in relation to that reference value. So that's our reference voltage, V2. We use a potential divider to set that one. All right, so once we set that one now, right, we can then look at our V1, right? And the V1, as we said, that one is what is being inputted into your non-inverting, right, input. And so that is your non-inverting input voltage. Okay. Whenever you see the plus here, you know that it's not going to be inverted. So it says a non-inverting input voltage. Okay. And so what did we say the V2 was? We said that the V2 was also gonna function as our reference voltage. So we're gonna compare our V1 to that. Okay, so that's our reference voltage right here. Okay, again, this minus is how I knew it would be the inverting input, okay? All right, so let's go ahead. So we have our reference voltage that we set using a potential divider. So now we're gonna compare V1 to V2 to know what is going on. Like that's how we do the comparison. So to do that, of course, we're gonna be using our trusty equation that we established up here from part I. And so here's how the equation is going to tell us what's going on, right? Basically, we want to know, is this bigger than this? Is this smaller than this? That's really what we're comparing, right? The size, or are they equal, right? Those are the three conditions. So here it is. V1 can then be compared to the reference voltage V2. So here are the conditions again, explicitly. V1 can be equal to V2, right? And if V1 is equal to V2, let's come back up here to our equation, right? If V1 and V2 are equal, guys, what does that mean? This whole thing would be 0. There would be no difference between them and it would be 0. So your V out would read 0. So if your V out reads 0, then you're like, oh, they're the same. Okay, they're the same. So remember, like you're not going to know what V1 is. You're going to be able to tell what it is based on what this readout gives. And if the readout gives you that it's 0, then you'll know that it was the exact same as your reference voltage, aka V1 is equal to V2. So that's the first condition, right? Well, that's the first thing that can happen, right? The second thing that can happen is that, you've already set your reference voltage, right? So say you set your reference voltage or your V2 to be 8. And you have a V1 that's greater than that. So say V1 is 9. What we're going to have is 9 minus 8. So in here, it's going to be 1. And so our V out is going to end up being positive, right? I think most importantly, it's that it's going to be a positive number that you're going to get here. And that positive difference between them is going to get amplified as seen here by this gain, which is generally greater than 10 to the 5 for a real op amp. This is generally greater than 10 to the 5. So if you're amplifying a positive 1, you're going to get a very big positive output, and it's going to saturate, right, the amplifier. And so we're going to see this value here. Okay, so when V1 is greater than V2, we're going to saturate and we're going to see our positive power supply value. So if you look on your output thing and you see that that you're positively saturated, then you will know that, oh, my V1 is larger than my V2. Whatever that V1 was that you put in is larger than your V2 because you see a positive saturation, right? So we call that positive saturation. And that's when your V1 is larger than your V2. Okay? So that's the second case that could happen, and that's a comparison. So that's one of the things that a comparator could tell us. Okay? All right. So let's look at the third case now. Let's look at the third case. Right? Let me just leave that there for now and take this one out. All right, so let's look at the third case. Again, let's assume I set the reference voltage to be 8. So my V2 is set as 8. If it is that my V1 is less than 8, so say for example, it is 7, which is less than 8, then when I look at my equation here, my V1 being 7 and my V2 being 8, what will I have inside here? I'll have a -1. Again, that -1 will be amplified times 10 to the 5, and I'll see a very big, right, from a mathematical standpoint, I'll have a very big negative voltage for my output. But that's going to get saturated to only being that, right? Because your output voltage can't be more than whatever the supply voltage is. And so because it's negative, it will become negatively saturated. And so you'll see what we call negative saturation in that third case, right? So if you ever see a negative saturation as your output voltage, then you know that your V1 was less than your V2. Okay, and so that's why you would have seen the negative saturation, or you see the negative voltage supply being shown as your output, and you'll know, wow, V1 was less than V2. Okay, so that's how the comparator works. I think the key points that you need to hit here is that of course, you're going to have to use the equation as your starting point to explain it, but then you have to run through the different conditions that are possible and what they would mean from a comparative standpoint. And then, of course, you have to say that you would establish your reference, right? Your reference voltage that you're comparing the other one to. Okay? And so with that, we're ready to move on to the other part of this question. All right. So the other part of this question now is asking us to do an actual calculation, right? So here it is. It's the very same setup, right? The very same setup. And it says the amplifier shown in the figure below has a gain. Here's that gain again. AV is equal to 10 to the 6th. And is powered by a supply voltage of plus or minus 5 volts, right? So that's your VS. So that means that this one can top out at plus 5, and the negative saturation would top out at minus 5. So that's literally what this means. Okay? So now we're being asked to determine the differential input voltage, delta V, that would result in what? A saturation with a negative voltage on the output. We just spoke about this. Okay? So we need to find a delta V that will give us a negative saturation. Okay? So the delta V, all right, so let's bring up our equation now, the master equation that we're going to use. Here's the master equation, this guy, that your V out is equal to your gain times the differential, or the difference in the input voltage, okay? So in essence, what that means is that this is what we're finding. This right here is what we're finding. That is our delta V. It's a differential input voltage. Okay, so effectively, what do we have then? V out is equal to AV times delta V. Essentially, that's what it is, right? And so we're being asked to find delta V. And so what are we going to do? Let's go ahead. We're going to say, okay, V out is going to be, if we need to find delta V, we're going to divide both sides by AV to make the delta be on a side by itself, right? Making that the subject. So I divide my V out by my AV, and that gives me V1 minus V2, which is my delta V. When I do that, I plug in minus 5 volts because it's a negative saturation. So I plug in this one right here for my V out because that's what we would see. That's what they're asking us about. So I plug the negative 5 volts here, divide that by the gain of 10 to the 6th. And then I'm going to come out with a value of delta V, or my differential input voltage, being minus 5 times 10 to the minus 6 volts, which is the same as minus 5 microvolts. When you really think about that number, guys, that's a really, really small number. You know, that's a really, really small number. But because your gain is so high, it saturates the whole thing. So we get negative saturation, we get negative 5 volts, okay? And that corresponds to a delta V of negative 5 microvolts. All right. And so with that, we're ready to move on. So let's go ahead now to the other part. All right, so we're at 2B now. It says that an intern at an aircraft manufacturing firm was told that to prevent icing of the aircraft wings during cold weather, the temperature of its wings should never drop below a certain value. She designed the simple comparator circuit shown in the figure below to trigger an alarm if the temperature of the wings drop below the threshold value. Right? So there's a value below. You don't want to go below that value because the wings will freeze. Okay? All right. So she has a comparator circuit that she designed here. So again, look at here. We see our inverting input. We see our non-inverting input. We see our positive saturation voltage and our negative saturation voltage. We see that we have an output here, and we see that this is connected to the alarm circuit. So that's whatever comes out is going to trip the alarm. Okay? So let's see now what is being asked in relation to this design. So we have to explain how the circuit in the figure below will function to trigger the alarm if the temperature drops below the threshold value. Right? So there's a threshold value, there's a temperature below which you cannot drop. So let's just write that as T threshold temperature. So let's just say T thresh. We cannot go below that. Okay, that's the minimum. If we go below that, the alarm is gonna trip. All right, so that's T threshold. Okay, temperature threshold. All right, so we have to explain how the circuit will function to trigger an alarm if we go below that. If we go below that, the thing is gonna alarm. How is this gonna function in that way? It's a comparator. It's a comparator circuit. So much of our discussion earlier about how a comparator works is gonna carry over. So here's what we would say. By the way, this question 2B is worth 8 marks. So think about that. You have to hit a bunch of points, and we're gonna hit them all right here. So let's go ahead. So the first point is this, right? A potential divider is used to fix the inverting input voltage, V minus, at the threshold value. This is the reference voltage. So what we're saying is that this guy here, we're going to use a potential divider to fix this. And that is fixed, that voltage that is going to be fixed at corresponds to the T threshold. So that corresponds to your threshold temperature below which you don't want to drop. And if you do drop, the alarm has to trip. So we're going to set that. We set that voltage that corresponds to the temperature threshold. Then what are we going to do next? So how is the alarm going to really work, right? The thermistor, so this guy right here, our thermistor, which feeds into, you see that? It's going to feed into this one, which is your non-inverting, right? This is your non-inverting input. So the thermistor feeds into the non-inverting input V plus, and the thermistor has a resistance that changes in response to temperature. So it's a temperature sensor, right? It's a temperature sensor. And basically what's going to happen then is if the temperature decreases, then the resistance of this thermistor also decrease. And if the resistance decrease, then what happens when the resistance decrease? Your current goes up and your voltage also goes up. So let's keep that in mind, okay? It's a thermistor, it's temperature, the resistance is dependent on temperature, and with temperature drop, the resistance is gonna drop, current goes up, voltage goes up. So keep that in mind. So here it is now, the thermistor, whatever happens to the thermistor is gonna get picked up directly by this non-inverting voltage here. It's gonna be reflected in the non-inverting voltage. So here's what we say next. We say, okay, when the temperature drops and it drops below the threshold value, the resistance of the thermistor also drops, thus resulting in the voltage that we see at this non-inverting input is going to increase, and it's going to become now greater than V minus. Keep that in mind. Let's go back to our equation here. V out is equal to AV, right? Right? That's what we always go back to. So what we're saying now is that this thermistor now, when the resistance drop because the temperature drop, the voltage is going to go up. So this guy's going to get big. So we're going to end up in a scenario where V plus is greater than V minus. Okay? So now what do we have? We say positive saturation, right? We have positive saturation now. So that means that this value here is going to be picked up by our circuit. The circuit is going to pick up, oh, plus 10, right? The system is programmed in such a way that when it sees plus 10, here it is now, a V out value of plus 10 is now registered in the circuit, right? And that is going to trigger the alarm. Okay? So keep that in mind. So keep what we're doing here in mind. It's a comparator, you know. So we're comparing this voltage that the thermistor sets, right? We're comparing that to the threshold that was set before. And if it is that this is now greater than my threshold, well, actually, the voltage is greater than my threshold voltage, right? Because the temperature dropped and made the thing less resistance and more conductive, right? And so the voltage goes up. Then the voltage will be greater than this voltage, and I'll have positive saturation. The system picks that up and the alarm gets triggered. Okay, so this is one to just definitely sit with and just make sure that everything is clear here. But really and truly, fundamentally, we're going to come back to this comparator equation. So make sure you have this one down and you know the three conditions that we would have discussed earlier. Okay, all right, so let's go ahead, clear this, all of this for 8 marks. Done, done, done. All right, moving right ahead now. Cascade amplifier. So the figure below shows a cascade amplifier circuit, right? So here's our cascade amplifier circuit. We have this resistor here. All of that there goes into that non-inverting input, and specifically the inverting input, the feedback goes into the inverting input, but your voltage, your input voltage goes into your non-inverting node right there. So keep that in mind. And then we see that now the output here is being fed into this inverting node here, and it has to pass through this resistor to do so. Then once we get the output here, some of it is fed back into the inverting node. So there's like a negative feedback in both cases, right? So that's what a cascade is made up of. We're gonna have the output of one of the amplifiers acting as the input for the other. That's what a cascade amplifier does. So we're being asked to determine the overall voltage gain of the circuit, right? So the overall voltage gain that we're going to get out of these amplifiers being cascaded like that. So here's how we approach this. So the overall voltage gain of a cascade amplifier circuit is going to be equal to the product of the gains of each circuit. So that is that the overall gain is going to be equal to the gain from this circuit, A1, times the gain from this circuit, right? So if this is my first circuit and this is my second circuit, this first circuit has a gain A1 and this second circuit has a gain A2. Okay? So when we look at A1, we need to find the gain of A1 and then A2 and then multiply them. So when we look at A1, what do we notice? We notice that our input is going to the positive port, positive node. So what does that mean? That means that we have a non-inverting amplifier in the first case, right? Because my input voltage is going to my positive node, it's non-inverting. It's a non-inverting amplifier that we have in the first case. And then in the second case, as I said, this output is gonna come in and flow into that node there, which is a negative node. So because that's negative where the input is coming into, what do we call that one? That is an inverting amplifier that we have. Okay, inverting amplifier. So when we're finding the gain for a non-inverting amplifier, which is what we're trying to do, A1, we're going to use this formula that says A1 is equal to 1 plus RF over R. Okay, my RF is the feedback voltage. So it's this one here. This is RF. That's the feedback voltage, right? That's the one that got fed back from the output here. And then this was just my original voltage here. We call that R. So I'm going to do 45 over 10 and I come out with 5.5 when I add that to the 1. We have to do that in a non-inverting amplifier case. We have to. That's the formula. So we have the gain of one of them. I need to find the gain of this one now, A2. When we look at A2, what did we say? It is an inverting amplifier, okay? This one is an inverting amplifier. And so to do that, to find the gain of an inverting amplifier, we're going to do minus RF over R. And my RF in this case, right? The feedback goes into this resistor. So it's RF. And that's 60, and then my regular R would be 6. So I do 60 minus 60 over 6, and that becomes minus 10, right? So I just found my A1 and I just found my A2, right? A1 turned out to be 5.5 and A2 turned out to be minus 10. So all I have to do is multiply them now and I have the overall voltage gain. Okay, so here it is. Finally, this is our final answer here. Is that A is going to be equal to 5.5, this one, times minus 10, this one, and that is minus 55. So that's my overall voltage gain for this whole circuit, this whole cascade. So that's our answer that we're locking in. Okay, This is our answer that we are locking in. Let me bring this up so you see it clear. Let me not cover my answer. This is the answer, guys, okay? Overall voltage gain. All right, so we're ready to move on. Ready to move on. But at this point, guys, you know what I want to say is I want to say something to you. You're watching this video, you know, hopefully this is helping you, but I really want you guys to subscribe. Take a moment, pause this video, pause it, go down, scroll down, hit that subscribe button. It would mean the world to me. And if you got this far and you're actually subscribing, definitely drop a comment, say something to me so I can know that this is hitting, that this is connecting, and that you've been helped tremendously up to this point. Okay? Now we're going to go ahead and we're going to move on to part D. So part D says, state what is meant by the bandwidth of an operational amplifier. What is the bandwidth? Right? Just think about that word, bandwidth. The bandwidth of an operational amplifier is the range of frequencies over which the gain of the amplifier remains constant. Okay? So it's a range of frequencies over which the gain of the amplifier is going to stay the same. It's not going to change over that range of frequencies. Okay? That's what we mean by bandwidth. All right. So let's go ahead. The figure shows a gain frequency response curve for an ideal operational amplifier operated in open loop configuration. When we say open loop configuration, guys, it means that there is no feedback. There's no feedback. Nothing is being fed back in. Okay, so there's no feedback here. It's like full open loop configuration that we're dealing with here. Okay, nothing is being fed back. And this is the configuration that we use the comparator for our comparator. So just remember that open loop. All right, no feedback. All right, so here's our gain frequency response curve. We have our voltage gain on the Y, and it's important to know that that's in decibels. Very, very important, okay? Voltage gain in decibels on the Y, and then on the X, we have frequency in hertz. Okay, make sure that you're paying attention to your units whenever you look at these graphs because, you know, they can be tricky. Okay? All right, so let's move ahead now to see what the question is on this. All right? So here's a question now. On the figure, insert each of the following labels, F sub C and F sub U, and say the numerical value of the frequency at each point on the graph. Okay? So the F little c is your cutoff frequency. And the cutoff frequency is that point on the graph where you're looking at the gain, and then all of a sudden you see like a massive drop in the gain. And that's at this point here. Okay? Gain is constant. Then you see a sharp drop. And that happens at 10 to the 1 frequency. So that is what we call your cutoff frequency. And so that's F little c. That's where the gain changes dramatically from being constant. So that frequency there, we would write 10 to the 1 hertz. Okay, that's our cutoff frequency. All right, unity gain frequency now. Unity gain means that we have a voltage gain of either 0 decibel that we can see on our graph, or again, a unitless gain of 1. And those two things are interchangeable, or they're equivalent. At 0 decibel, there's a gain of 1. So we're going to look on our y-axis, and we're going to see 0 decibel. 0 decibel is right here, right? So what we're going to do now is we're going to come across. We're going to come across to see what frequency that corresponds, and we see that it corresponds here, right? At a frequency of 10 to the 6, we have 0 decibel or a gain of 1. That's unity. Unity means 1. A gain of 1, which is the same as 0 decibel. So it's happening here at this frequency here, 10 to the 6th hertz. So that's our unity gain frequency at 10 to the 6th hertz. So my answer here is 10 to the 6th hertz. Okay? That's the answer we'll be submitting here. So that's my unity gain frequency, and this is my cutoff frequency. All right, and so we're done with this part of the question. All right, so let's go ahead to this part now. which says determine the gain of the amplifier at 1 kilohertz. Okay? No, remember, we said earlier, we're looking at our graph and we want to be careful about our units. This gain is in decibel and this frequency is in hertz. They're asking us to find the gain of the amplifier at a frequency of 1 kilohertz. And so what does kilo mean? 10 to the 3. So really what we're looking for is 1 times 10 to the 3 hertz on our graph. Okay? So let me just populate what I had there. So 1 kilohertz is the same as 10 to the 3 hertz. And at 10 to the 3 hertz, we see that the voltage gain is 60 decibels. So let me just go up to that. Let me just get my pen and go up to that. So we're looking for 10 to the 3 hertz, which is here. And I'm going to come up, meet my gain frequency response curve. I'm going to come across and find the gain that corresponds to that frequency. And it turns out that it is 60 decibel. Okay, guys, this is a question that is worth 3 marks. It cannot be that easy. It cannot be this easy. So we're not done. We're not done. This is in decibel. We're going to have to put it in the unitless form. Okay? 3 marks. We're going to have to do some more work. Put this in the unitless form. And so we must convert the decibel to the unitless gain that we're used to, right? And we spoke about that earlier when we were finding AV, right? And we said that the AV, right, would be equal to the V out over the delta V, right? Delta V in. That's what we said earlier. That's how we would calculate gain. Remember that. So we need to find this version of the gain, right? We have the 60 dB and there's a connection between the decibel and this version of the gain. So let's see what that is, right? This is our connection. So whenever we are given a gain or we just found a gain in decibel like we did here, it's going to be equal to 20 log to the base 10 of your V out over your delta V in. Okay? So we got 60 decibels from our work here. So we're going to plug the 60 decibels here. Plug the 60 decibels here and just equate that to the right-hand side here. Remember, our objective is to find this V out over delta V in. That's the regular gain that we would use, right? So that's the one that they want us to find for 3 marks. So this is my objective. So I'm isolating everything to make this be by itself because that's what I want to find. And so I'm going to do 60 over 20 is equal to log V out over delta V in. So I'm going to end up with 3. 60 divided by 23. 3 is equal to log to the base 10 V out over delta V in. So then now all I have to do is undo the log. So I'm going to do 10 to the 3, which is the same as 1,000, is equal to V out over delta V in. And this is our final answer. That's what we're expected to do for this whole 3 marks here, okay? So that's what they want us to find. That is the gain of the amplifier, 10 to the 3 or 1,000. Okay, at 1 kilohertz, which is 10 to the 3 hertz. Okay, and so with that, we've come to the end of this question. Definitely give this video a like, subscribe to the channel, and if you look on your left here, you'll see the next video up, and if you look on the right, you'll see the Module 2 playlist, where you'll find tons of more interesting content that would be very helpful in getting you prepared for your exam. So thanks for watching, and we'll see you in our next video.